Alright, let's do some derivatives. So this is a good first problem for this section because this is just a lot of practice of just doing the basic computations to get you familiar with the flavor of how the problems in this section go, and then once you're good with these types of things, then you can start moving on to thinking about the more difficult problems. But let's see here. So what we're doing here is we have to sort of solve these problems in weird ways. Like maybe if you've taken a multivariable calculus course before, or if you've looked ahead at all in this section, then you know that how these problems usually go is if you want to find the derivative of a function from Rn to Rm, what you have to do is you have to you basically build a matrix, and each row in the matrix will tell you which of the component functions you're looking at, and which column in the matrix you are tells you which variable you're taking the partial derivative with respect to. And you use this procedure and you can sort of build a matrix in this way, and it's really straightforward. But for this problem, it's what you have to do is we don't have that theorem yet. So what we have to do is, let's see here, we have the chain rule. That's very important. And we were able to prove the addition rule and the product rule. And, well, the quotient rule is sort of just another sort of the addition rule, or another sort of the product rule. And then we also can work with projection functions. So we need to use those tools to our disposal and rewrite these functions that we're looking at in terms of those components. Alright, so let's take a for example. So we've got this function, it's just x to the power of y. Now, of course, you could just replace x with, well, here, let me show you what we have to do. The easiest way to deal with exponentials, or something being raised to another power, is to write these in terms of exponentials and natural logs. So instead of taking this as x to the y, this is the same thing as e to the natural log of x to the y. And then, because of how natural logs work, we can bring that y down front. So this is e to the power of y times natural log of x. Okay, so now what we want to do is, and of course, I'll rewrite this as e to the power of y natural log x will be the same thing as exp, and then in parentheses you could just put y natural log of x. Now, you want to imagine that every input into this final formula should be a vector. So if you're inputting a vector and you want to end up with y, then it needs to be y. Here, I'll write this as pi 2 of, and then x with the bar over it, and then times natural log of pi 1 of x with the bar over it. So here, x bar, here I'll just write this, x bar is going to be equal to x, y, and z. So in this final formula that we're ending up with, we need to have things that we can differentiate, meaning things like exponential functions, natural log functions, multiplication and addition and subtraction, and things like that, things that we know how to differentiate. And we also need to have, we need to make it so that the thing that we're inputting is the same type as the domain of the function. So this is a function whose domain is R3. So the inputs for this function need to be vectors in R3. And so, therefore, we want the inputs to be x bar, where x bar equals x comma y comma z. And so in order to extract the y and the x from this, we have to use pi 2 and pi 1 to project, to take this vector and use projection to extract one of the components. Okay, so now we've written this function in the way that we want. So now what we can do is we can take the derivative of f, and we're going to take the derivative at a comma b comma c. because if you take the derivative at a point, then you get a function. And so basically we're going to take the derivative of f, and the variables that we're using are going to be a, b, and c, because those determine which point we're taking the derivative at. Okay, so now what this becomes is I'm going to now start using primes, because if you use primes, it makes it a little easier, in my opinion, to understand exactly what thing is in the scope of each derivative. So first we take we have to do the chain rule here, because this is the exponential of a function on the inside. So, and now I'm not going to include like the x bars at all. So I'm just going to write pi 2 times natural log of pi 1. Where it's sort of understood that when I write pi 2, I mean pi 2 of the vector x bar. And when I write natural log of pi 1, I mean natural log of pi 1 of the vector x bar. Okay, so we take the derivative of the outside function, then we have to multiply by the derivative of the inside function. So I'm going to take pi 2 times natural log of pi 1, and we're going to put a prime. Okay, now the next step, now when you take the derivative of the exponential function, nothing changes. So we're just left with exp, and we have pi 2 times natural log of pi 1. Since we don't have any more differentiating to do on the inside here, we can go ahead and replace all these projection functions with what you would get when you plug in the vector a comma b comma c. So if you plug a comma b comma c into the function pi 2, you'll just end up with b, because you're just extracting the second coordinate. And similarly, we'll get multiplied by natural log of a. And now here, we've got pi 2 times natural log of pi 1. So here we have to use the product rule. So we'll start with take the derivative of pi 2 and multiply by natural log of pi 1. Then we add pi 2 times, and then we'll take the derivative of the natural log of pi 1. Alright. So now what are we doing? Okay, so now if you look at this, the exponential of b times natural log of a, we basically are going to end up going backwards to this, from this to get back to the same thing that we started with. So what you could do is you could take the b and raise it. This is the thing on the inside is the same as natural log of a to the power of b, and the natural log will cancel with the exponential, and you'll end up with a to the power of b. Now moving here, now the derivative of pi 2 is 0, 1, 0, because remember the derivative of pi I is just a vector which is zeros everywhere except for a 1 in the ith coordinate. So that's why you get 0, 1, 0, and we multiply by the natural log of pi 1, which we now can write natural log of a. And now we're going to add, it's here pi 2, so that's b times, and now we've got natural log of pi 1 prime. So now to do that, we have to do the chain rule. So we start by taking, well, the natural log of x is 1 over x, so the natural log of pi 1, we're going to get 1 over pi 1. Then we're going to multiply by the derivative of the inside, which is the derivative of pi 1. Okay? So now, we got a to the b, and now if you take 0, 1, 0, multiply by natural log of a, you get 0, natural log of a, 0. Plus, and now we've got b times, and then 1 over pi 1, well, pi 1 we can go ahead and evaluate that to a. So this is going to be b over a, and we're going to multiply by pi 1 prime, so that's 1, 0, 0. Okay, so now we have a to the b times, we've got 0, natural log of a, 0, and we add b over a. Well, we can go ahead and combine this into 1. This is going to give us the first coordinate is going to be b over a, the second coordinate is going to be just natural log of a, last coordinate will be 0, and then, yeah, so we have this, and then if we want to go ahead and write this further, we have a to the b times b over a, the first coordinate, and then a over b times natural log of a in the second coordinate, and then 0 in the third coordinate. And there we go, that's all we need to do for this one. And let me just make sure that that agrees with what I have written, and it does. Okay, so that's the basic idea of how you do these types of problems. And then let's just do b as well, because b follows very quickly. Because this is what we have to do for b. b is f of x comma y comma z will be, let's see here, we have x to the y comma z. Okay, so the way that this works is that when we take the derivative of f, and again we're evaluating at a comma b comma c, this is going to be a matrix, and it's going to be a matrix whose first row is the derivative of the first function. So the derivative of the function x to the y, and of course we're evaluating this at the point a, b, c. So that's the first coordinate, or that's the first row. The second coordinate, the second row is you take the derivative of the second function in here. So this is going to be the derivative of the function z, and this is a, b, c. Again, being evaluated there. Okay, so finally what we end up with is we end up with a matrix. And so the first row is going to be, well, we already did that in part A. It's just going to be a to the b times b over a. That's going to be the first column in this first row. Second column will be a to the b times natural log of a. And the entry in the third column will be 0. And then for the final function, well, the third function, the function in the second coordinate it's just pi 3. It's just projecting the third coordinate, and the derivative of that is obviously 0, 0, 1, and so the final row here is just 0, 0, 1, and of course the point ABC does not matter here for this final row. But yeah, so that's how you do part B. And so this should give you sort of an idea of how to approach all of these types of problems. As you see in part A, if you've got a function, you have to rewrite it in a way using addition, subtraction, multiplication, exponentiation, natural logs, and projections, and then use all your differentiation rules to get the actual derivative. And then if you have a function which maps not into R but into like Rm for some m greater than 1, then you just have to do each function one at a time and combine the answers into a matrix. And so we will continue these techniques to finish out the rest of the parts of this problem.